So question number 1 on your exam next Thursday is going to be one of these two types for sure, and there's a decent chance you'll see the other type somewhere. First one is launched like this. The second one, the object, the ball, whatever, is launched like this. It doesn't matter which one you see. In both cases, we're going to break it up into x components and y components. The x component is always described by which equation? You will write this down in question number 1. If you don't, okay, you should give yourself a kick in the butt because I'm telling you, this is question number 1, and you need to write this down. Okay, the first equation that we're going to write down next Thursday on that exam is what? V equals delta D over delta T. The second equation that you're going to write down is what? D is equal to what for the y component? Yep. Good. D is equal to VIT plus 1/2 AT squared. It doesn't matter whether it's the first one or the second one that you see. Okay, launched horizontally or launched at an angle, those will be the two equations that you need to use. Now, when we determine which one it is that we have, whether it's launched horizontally or launched at an angle, some of the things within these equations become a little bit different, but the general strategy is still the same. Okay, let's say we're launched at 10 meters per second here from a height of 20 meters. Okay, we want to find out how far it travels. Let's see, here we're launched at 10 meters per second at an angle of 30 degrees, and then of course it comes back down to its initial level again. If we're plugging in, let's make that problem number 1 and this one problem number 2. Okay, if we're plugging in the data from problem number 1 in a horizontally launched problem, then V in this case will be 10 meters per second. We don't know what delta D is. We don't know what delta T is. D in that case for the y component is negative 20 meters because it ends up 20 meters below where it started. VI is 0, so VIT is 0. We add that to 1/2 of negative 9.81 times t squared. So we end up solving for t here, get a value for it, plug it back into here, and we solve for the displacement. That's if it's the green problem. That's if it's the problem where the object is launched horizontally off the edge of the building. Okay, it's not that hard. We don't have to deal with any kind of funny angles. We don't have to deal with any kind of tricks here. They're always the same. You may be solving for a different variable. Okay, but in the end, if you're solving for V instead of delta D, well, then you would have to be given that value, and you just would have subbed in different expressions, that's all. Solve for something different. It's just a different rearranging, that's all. Good question? Okay, let's deal with question 2 in a second, okay? We'll get to it. Now, the second question, same basic 2 equations that we start off with, but the way that we analyze it is slightly different here. What's V for question number 2? What's VI for the x component? We don't know, do we? We don't know what it is. It's not 10 meters per second. I'm not going to write down a red at 10 meters per second. Problem number 2. Rather, we've got to get rid of that funny angle. That funny angle. We don't like funny angles. Let's get rid of it. This is 30 degrees. This is x. This is what? We've done this a million times before, right? Let's say cosine 30 degrees is equal to x over 10 meters per second. Sine 30 degrees is equal to y over 10 meters per second. X ends up being equal to 8.66. Y ends up being equal to 5. All right. So now if we're doing the red problem, the second problem here, then V is what for the x component? 10, 8.66, or 5? 8.66. We don't know what delta D is for the x component, for the x or for the y component. For the problem number 1 or problem number 2. Nor do we know what delta T is. Let's go to the y component. Do we know what delta D is for the red problem, the second problem here? Somebody else raise their hand here, please. Go ahead. Good. It's going to be 0 meters. It goes up and it comes back down. Okay, I don't care how high it goes, or I don't even care what path it takes. We know it's parabola that it takes, right? But that's really irrelevant for determining delta D for the y component because it ends up where it started on the y-axis. So delta D for the y component is 0. Notice it's different. It's different than it was for the x component. It was neg 20. Sorry, it's different than it was for the first problem. It was neg 20 for the first problem. It's 0 for the second problem. VI for the y component in the first problem was nothing. VI for the y component in the second problem is 5 meters per second. Now we solve for t the same as we did with the green problem, the first problem. But this time it's a little bit trickier actually to solve for t. So I'm going to help you with this one. What we can do here is cancel out one of the t's. Everything gets divided by t. 0 divided by t is 0. 5t divided by t is 5. Half neg 9.81, that's neg 4.905. T squared divided by t is t. Let's take the 4.905 to the other side. T equals 1 point something, whatever it works out to be. Plug it back into here, and then we solve for the horizontal displacement. Travis? Why did I take out t? Because I have no other way of solving for what t is. It's in two places. I can't solve for t when it's in two places. How did I get it out? Okay, I said I divided everything by t. What's 0 divided by t? 0, right? What's 5t divided by t? 5. What's neg 4.905 t squared divided by t? Neg 4.905 t. Does that make sense? How did I get rid of the 4.905? I took it to the other side by dividing. 5 divided by 4.905. Yep. Yes, we'll go to that, though. We'll go to that. So the basic part of the problem is this, right? If it's launched horizontally, you're looking at green. If it's launched at an angle, you're looking at red. Almost the same. There's only a couple small differences. Our differences are this, first of all. Here we get 10 meters per second launched horizontally. We have a component of 10 meters per second if it was launched at an angle. The initial speed was still 10, but we don't want the 10. We want the horizontal component of that. The second difference was this. The vertical displacement in the first case was neg 20. It ended up below where it started. The vertical displacement in the second case was 0 because it landed up where it started, vertically at least. It ended up where it started. And then the third difference is this. The vertical velocity for the first problem was 0 because it was launched horizontally. The vertical velocity for the second problem was a component of the 10 meters per second, ended up being 5 meters per second. Everything else is the same. Okay, so remember those three differences between those two types of problems. It doesn't matter what you should be able to solve that problem. Okay. Now, what else could we ask here? Somebody asked just a minute ago, Jay said, could you ask us for maximum height? Absolutely, I could ask you for maximum height. Okay, if I ask you for maximum height in the first problem, the green one, it's easy. It is the most ridiculously easy question ever given. In fact, so easy that I don't think I've ever given it. If I was to give it, the answer would be what? What would it be what? 20. If it's launched horizontally for 20 meters high, it's not going any higher. The max height is 20 meters, okay? If I did give you a question like that, maybe as a multiple choice question or something like that, hey, don't look a gift horse in the mouth, just accept it. Say a little prayer of thanksgiving for such an easy question, and then move on to the next one, okay? What if I ask you for the maximum height in the second question? It's not brutal, but it's certainly harder than it is in the first one. Okay, what would I do for that one? Okay. We would solve for D, now that we know T, solve for the vertical. We know what vertical is, it's 0. Yeah? Okay. Rutger just made a mistake. He thinks he's right now. And it's a good guess, actually, Rutger. But it doesn't work. Rucker just said, use the time we just found, plug it into the equation, d is equal to VIT plus 1 half AT squared, okay, and then solve for d. What do you think we're going to get if we plug in this time into this equation, d is equal to VIT plus 1 half AT squared, and solve for d? What do you think we're going to get for displacement? 0. Because we would have to divide that by 2, yes. Now, that's not the way that I suggest to doing this question, but it works, so that would be absolutely fine, Rucker, okay? Absolutely fine. Rucker said, Rucker's change here is in his method now is, let's divide this time by 2. If we divide this time by 2, then we can plug it back into this equation, solve for the vertical displacement. That will give us our max height. Personally, I think the easier way to do this, though, is to use this equation. VF squared is equal to VI squared plus 2AD. Okay, remember, you got to do that for the vertical. Horizontal, you can't use a group B equation. It's got to be group A, B equals D over T. So this has got to be the Y component. Let's solve for D. Let's solve for D. Delta D is equal to VF squared minus VI squared divided by 2 times A. Now VF, vertically, as it goes up vertically, what's VF? At the max height? 0. So let's say 0 squared minus VI squared, which is 5. The Y component of the initial velocity is 5 meters per second over 2 times 9.81, neg 9.81. And whatever that works out to be, that is our maximum height. Okay, so
Negatives.
yes, that's right. It would be. So it's negative 5 squared becomes negative 25 over negative 20 about, which ends up being somewhere in the range of positive 1.25. Okay, somewhere in that range of positive 1.25. It would work out to be positive, and of course it should, right? You're looking for max height. You're not going to get a negative value for max height. It's got to be a positive value. What else did I tell you was going to be on this test? I said we were going to get either a position time graph or a velocity time graph. That was question number 2. Position time graph would look something like this. Maybe you got some numbers in a shape that looks like this. Okay, a velocity time graph, maybe it looks something like this. Same shape. Let's make it the same shape. Let's put some numbers on here, okay? Just for argument's sake here. Let's make this 10. Let's make this 30. Okay, let's make this 10 and 30. Let's make this 5 seconds, 10 seconds, 15 seconds, 5, 10, 15. Haven't drawn that to a very good scale, but that's okay for purposes that we're doing here today. Okay, what can we find from these things? They look like the identical graph. Well, we're going to analyze them the same way, right? We're not. Okay, what are we going to find for the first one? Well, maybe the first one, I ask you for the position at 5 seconds. The position at 5 seconds is what? Well, the only thing we're going to do to get the position at 5 seconds is to go up and over. So we go up, we go over, the position at 5 seconds is 30 meters. That's easy enough, right? What if I ask you for the position at 15 seconds? Well, that's even easier because at 15 seconds it goes through the x-axis, so the position at that point is 0 meters. What if I ask you for the displacement between 5 and 15 seconds? Well, displacement is a change in position, right? So if we've got the position at 5 seconds, the position at 15 seconds, let's subtract the two. 0 minus 30 gives me neg 30 meters per second. No, just meters. Just meters. What else could I ask you here? What's the velocity at 8 seconds? How fast is it moving at 8 seconds? Let's go up here, right? 8 seconds, about right here. How fast is it moving up here? It isn't moving because it's a flat horizontal line. We know that that means it's at rest. The position isn't changing. So the velocity at 8 seconds is 0 meters per second. And we don't have to do a calculation for that. Just look at the graph. It's not moving. I could ask you for the velocity at 3 seconds. That's a little bit trickier. Okay, we got to do a calculation for this one. The velocity at 3 seconds is going to be found by either taking the slope of that graph or using v is equal to delta d over delta t. Delta d would be 30 minus 10. That's the final minus the initial for that interval over 5 minus 0. Okay, that's the final minus initial time for that interval. So delta y over delta x or delta d over delta t. That gives me 4.0 meters per second. That's the velocity anywhere between 0 and 5 seconds, including at 3 seconds. Maybe in that question I ask you for the acceleration. At, let's make it 13 seconds. What is it? We're not changing velocity, right? It's a constant velocity. It's a constant negative velocity at 13 seconds because it's sloping downwards, but it's still a constant velocity, so the acceleration at that point would be 0 meters per second. What if I ask you for the average velocity over the entire trip? Well, for that one, we're going to say v is equal to delta d over delta t, as we always do. Delta d for the entire trip is, well, we start off at 10, we end off at 0. The displacement would be negative 10 divided by the time of 15 seconds. It would be negative 0.67 meters per second. Well, does make sense? There's not really much else I can ask you for this. Okay, if all 7 of those make sense, if you get a position time graph on your exam as question number 2, you should ace it. If one of them doesn't make sense, then that would be a good time to ask me a question about it. Okay, good. The acceleration is 0 at 13 seconds, right here, roughly right here at least, because it's a straight line. A straight line on a d versus t graph means it's a constant velocity. And if it's a constant velocity, it's not speeding up or slowing down. So a would be 0. That make sense? So we're not doing a calculation to get a equals 0 there. Okay, we're just looking at the shape of the graph and recognizing that the acceleration has to be 0. Okay? All right, let's take a look at the second graph then. Second graph is a velocity time graph. What could I ask you for in this one? Well, I could ask you for the velocity at, let's make it 8 seconds. You're just going to go up and over 30 meters per second. What if I ask you for the velocity at 15 seconds? Tell me what that is, please. What's the velocity at the very end of this problem? Josh? 0. It's at rest now. It's come to a stop. What if I ask you for the change in velocity? Between 8 and 15 seconds. Is it 30 minus 0 or 0 minus 30? Final minus initial, right? What if I asked you for the acceleration at 6 seconds? Quick answer here. We don't need any kind of long, complicated analysis. What's the acceleration at 6 seconds? 0, because It's a flat horizontal line on a v versus t graph means it's going at a constant velocity, Travis. I will, yeah, I'll get to that, yeah. What if I ask you for the acceleration at 3 seconds? Well, for that one, it's a straight line, but it's a v versus t graph, and it's not a horizontal line, so we got to do something else to find that. Delta v over delta t. Delta v is 30 minus 10 over 5 minus 0. That's going to be 4.0 meters per second squared. That's the acceleration anywhere along that line, including at 3 seconds. What else could I ask you? I could ask you for the displacement, okay, over the entire trip, the total displacement. This one's a tricky one. Travis, how would I go about finding that? Yes, you got to find the area, and you got to break it apart to find that area. So let's do this. Let's break this into a triangle over here. Yeah, rectangle right there, and a triangle right there. Doesn't matter what order we call them in, or it doesn't even really matter how we break it up, because as long as we break it up into recognizable geometric shapes. 1, 2, 3, 4. We got to get the total area there. So let's say A1 is equal to my 10 meters should be right here, right? A1 is going to be base times height. 10 times 10 is 100. A2 is 1/2 of base times height. The base here is 5 for the second section. The height goes from 10 to 30, so it's 20. It's going to be 50 meters. The third one, we're going from 5 to 10 for the base. So that's a base of 5. The height is 20 again. That's going to give me 100 meters. And in the area of the fourth one, it's a triangle with a base of 5 and a height of 30. Now that gives me 1/2 of 5 times 30 is 75. We add those up. What do we get? 200, 250, 325. So the total displacement here would be 325. Man, if you ask for total displacement, you better hope it's a position time graph, because it's a lot easier, right? Position time graph is just final minus initial. For a velocity time graph, it's that total area, which is a lot more ugly. Fraser? Would you get a curved displacement time graph? You could. It's conceivable that you could. But if you did, there wouldn't be anything you would do with that calculation, with that curve in terms of a calculation. Okay? If it looked something like this, I may ask you for the displacement in the first interval. Well, it would be final minus initial, same as it was over here, right? I may ask you for the position at a certain time. Well, up and over, same as you did right there. But there wouldn't be anything you do with that curved line in terms of the calculation. No, not with the position time graph. No. Here's a rule of thumb. If you're asked for the acceleration on a position time graph, it's going to be 0. Because, you can get an acceleration on a position time graph, but there's no way for you to determine it unless it's a straight line. Okay? And then it's going to be 0, right? So I can ask you for the acceleration over here, and it can be whatever. But over here, unless it's a curved line, it's got to be 0. And if it's a curved line, you don't know how to find it. Yeah. What if it's curved on the velocity time graph? Well, then that would just mean that not only is it accelerating, the rate at which it accelerates is increasing as well. And it would be the same kind of thing as it was in the position time graph. There wouldn't really be much we could do with that curved line. Okay. you could go up and over and do some subtraction, but you wouldn't do a real calculation with that. Okay. There's one more thing that I could ask you here for the blue one, the second one, and that's the total displacement. Sorry, the average velocity, I mean, for the entire trip. If we're going to do that, we'll do it the same way as we did it for the last one. V is equal to d over t. But this time my displacement isn't found quite as easily. We have to do the area. It'd be 325 in this case over the time, which is 15 seconds. So what does that work out to be? 325 divided by 15 is 21.67. 21.7 meters per second would be the average velocity. So we get 7 things on both sides, 14 things. Who's comfortable with all 14 of those things? You guys should have, by this point on your test, okay, out of, what did I say, 80, 88, 90 points, something in that range, you guys should have approximately 15 to 18% of your test answered correctly, 100%. Okay, and that's not small. Okay, I mean, I know you don't want to go home with a 15 or 18% on your Physics 20 final exam. You want a higher mark than that. But look, if we can do the first 2 questions and be given kind of a head start with 15 to 18% of the exam, then I think we should work hard on that. Okay, you need to know these things. Okay, Travis? That's what I'm talking about here, yeah. There's 25 multiple choice, and then there's 10 written response. Basically, these are the first 2 written response questions. Projectile motion, either launched horizontally or launched at an angle, and then a graphing question, either position time or velocity time. Even if you can do them, then you're set for almost 20 points, almost 20% of your exam. Okay. What else are we going to see on there? Bailey just suggested that we might see a multi-force problem. That's from Unit 2, right? That's from our dynamics unit. Okay. That's what we spent most of that unit on, was multi-force problems. Okay, that could be something like, something as simple as this. Here's an object with a force pulling it this way. We'll call it FA, 10 newtons. Force pulling it this way, FB is 15 newtons. Another force pulling it this way, FC is 5 newtons. Okay, it could be something as simple as that to something as complicated as maybe this. Where you've got a mass of 20 kilograms here. Maybe you got a mass of 20 kilograms here as well. Okay, maybe you got a force of friction here. Let's not make it 20 newtons. That's going to get confusing. Let's make it 15 newtons. You have force of friction of 15 newtons, and we want to find the acceleration. Okay? Or it could be somewhere in between, right? It doesn't have to be one of these 2 questions. It could be something in between this as well. Okay? How would we solve this question? Well, F net is equal to the sum of the forces. It would be FA plus FB plus FC. We did a mass here, by the way. Let's make it 10 kilograms. The net force is M times A. Well, that's equal to FA plus FB plus FC. M is 10. A is whatever. FA is 10. FB is 15. And FC is 5, right? Is that right? Is that all right? No, it's not. What's wrong? Sorry? Well, there is a normal force in gravity. You're right about that. But if it's on a flat horizontal surface, it's not moving up or down, the normal force and the force of gravity, they're going to cancel each other, right? So we haven't paid any attention to those. We didn't really need to, although we really should have drawn them. You're right. Travis? Or Fraser? Yeah, something should be negative here. Usually we make what's to the left negative. In that case, we make the 15 and the 5 negative. Although, if you made those positive, it would be okay to make the 10 negative. It doesn't really matter there. Okay, 10 plus neg 15 plus neg 5 gives me neg 10. A is going to be equal to neg 1.0 meters per second squared. Could you get a question like this there? Absolutely. Absolutely you could. Take a look at the next one. Put an angle of 30 degrees in there. Could we get a question like this? Absolutely we could. Okay? You will see either this or something in between, right? Something involving more than one force acting on a problem. Okay, it could be just a straight pulley problem like this. It could be just a straight inclined plane problem like this. Okay, it could be just a straight problem like we saw over here. It could be, there's all kinds of possible combinations there. But basically, you're going to get one of those multi-force problems that we looked at back when we did this unit. Yep. One of the suspended problems. Oh, no, you will not. No, you won't. I won't give you one of those. Okay, so how do we do this one? This one's a bit of a problem because we've got an angle there at 30 degrees, right? And we don't like any funny angles, right? So let's get rid of it, basically. Now, how to get rid of this one? This one's a little bit trickier. We've got a force of gravity acting down that's equal to m times g. We've got a normal force acting at 90 degrees. This angle right here becomes 30 degrees. This force right here, we're going to call FH, the force of the hill. And that force we can also draw right here and label it again FH. We need to get the value of FH. We need to get the value of the force of the hill there. We're going to do that because it's the opposite side of the triangle. We're going to say sine 30 degrees is equal to opposite FH over m times g. So FH is equal to m times g times sine theta, which is 20 times 9.81 times sine 30 degrees. 20 times 9.81 times sine 30 degrees would be 98.1 newtons. We also, by the way, have a force of gravity that acts down on this. It's going to be 20 times 9.81, which is going to give me 196.2 newtons. I like to straighten these out. Some of you guys don't, and some of you guys are good not doing that. Okay, but if you're having trouble at all, then do what I do. Straighten it out. We've got a 20 kilogram here. We've got a 20 kilogram here. We've got a force of gravity now pulling it to the right. It's not really, but we're pretending it is. We have a force of the hill pulling it this way to the left. And we have a force of friction acting which way? It's 15 newtons, but which way does it act, left or right? Force of friction acts to the right? It's got to act to the left, right? Why to the left? Yeah. It's moving up the hill, right? And why is it moving up the hill? Yeah. Yeah, that force is bigger than the other force, therefore it's going to move that way. And if it moves that way, friction has to act the opposite way. Now this isn't any different than this one, right? We had to turn it into that first problem. But in the end, if you remember back in October, November, we always turned them into straight problems like this. Doesn't matter what we had, whether it was an elevator problem or even a vertical circular motion problem. In the end, it became an F net is equal to the sum of the forces problem. Okay, we always turn it into this. Here, F net is equal to FH plus FF plus FG. F net is equal to m times A And M would be 40 in this case. FH is neg 98.1. FF is neg 15. Fs is 196.2 newtons. Solve for A. It would be, what would it be? 2.0775. How's that one? The question was, how do you get 98.1? That's the force of the hill, right? And the force of the hill came up here by drawing this vector diagram we see in black here. Gravity acts down, normal force acts perpendicular to the surface. The force of the hill acts perpendicular to the normal line or parallel to the hill itself. Okay, we see here that the force of the hill is the opposite side of that triangle. We have the angle there. We have the force of gravity. So let's say sine 30 degrees is equal to opposite over the hypotenuse. And then we're going to solve for the opposite side. Works out to be 98.1 newtons when we multiply those numbers together. What do we use for mg? M is 20 and g is 9.81. M is not 40 because the force of the hill isn't acting on both of those, right? The force of the hill is acting on one of those. You will get something like this as question number 4 on your exam. So we know what question number 1 is. We know what question number 2 is. Question number 4, well, we pretty much know what it is, right? Is it going to be a straight problem like this? Is it going to be a straight problem like this with an inclined plane and a pulley? Is it going to be just a pulley? Is it going to be just an inclined plane? Is it going to be an elevator problem? Okay, I'm not telling you. I'm not giving you that much detail on it. But in the end, if you could do something like this, you're probably okay because this kind of combines a bunch of things, right? This kind of combines the straightforward thing with the pulley thing, okay, with the inclined plane thing. The only thing it doesn't really cover is the elevator thing. And in the end, an elevator problem is basically like this, except it's vertical instead of horizontal. So we can answer that one as well. The only thing with the elevator is remember that when we're asked for the apparent weight, what are we really looking for? The normal force, right? The normal force. Yep. Usually, in this one, you mean? Yes, yeah, you are. Yeah. In most of these problems, you are looking for the acceleration, although I suppose given the acceleration, you could find something else, but usually it's that way. So let's take a look at what I've told you here already. Question number 1, I told you was a projectile motion question. Just looking at some point values here. We are at a grand total at this point of what I've not exactly told you, but essentially told you, 22 points. 22 points out of 80-something or 90-ish, 91, whatever that was. What is that, 25% of the exam, 28% of the exam? Something like that? Yeah, it's a good fighting start here. Fraser?
It's going to be a question of
there could be. Yeah, absolutely, there could be. I'm not going to give you everything, right? I'm not going to tell you everything that's on there, but coefficient of friction. Coefficient of friction is absolutely fair game. I mean, pretty much anything we did is fair game. But I mean, we spent some time on that, so there's a decent chance that you could see something like that. If it's a more complicated question, it could appear as a written response. If it's a simpler question where here's the coefficient of friction, here's the mass, what's the force of friction, that could be something like multiple choice, right? The most simplest form of the question involving coefficient of friction would be, let me review just a little bit first, and then I'll ask you one, okay? There's 2 types of coefficients. There's the coefficient of static friction, and there's a coefficient of kinetic friction. Static friction will be bigger than kinetic friction. Okay, the coefficient of static will be bigger than the coefficient of kinetic friction. It's harder to get something moving than it is to keep it moving. Now, there's 2 equations that we learned here, or one of them is an inequality, actually. The force of static friction is less than or equal to mu times Fn. The force of kinetic friction is equal to mu times Fn. Why the difference here? Well, because static friction changes. Static friction isn't a fixed number. Okay, if I push on this desk, I push on Olivia's desk, 5 newtons, doesn't move, then static friction was 5 newtons, pushed back on me with 5 newtons. Okay, I push on it with 8 newtons, doesn't move. Static friction was 8 newtons. I push with 12 newtons, doesn't move. Static friction is 12 newtons. Push on it with 15, it does move. Well, now I've got kinetic friction, right? I've exceeded the maximum force of static friction. Static friction, you can see, changed its value. It was less than or equal to the biggest possible value. Now, honestly, these two equations appear on your data sheet, but you're going to use this one or this one that doesn't actually appear on your data sheet. FSF max is equal to mu times the normal force. Okay, get that value. If you get the value of mu times Fn for static friction, then that is right here your maximum possible value. Whatever friction you have has to be less than or equal to that number. So for instance, if I multiply this number by this number and I get 50 and I push with 30, then friction is 30, not 50. Friction is 30. If I push with 40, then friction is 40 because it's less than or equal to 50. If I push with 49, then friction is 49. If I push with 50, then friction is 50 because it's less than or equal to the maximum value that we just found. If I push with 51, all bets are off. I don't have static friction anymore, right? I have kinetic friction because now it moves. So now what I'd have to do in that case, say, go back and calculate the force of kinetic friction. So if you push it with a certain force that's below this value right here, the maximum possible value, then it will not move, and the force of friction will be simply whatever force you apply to it. If you push it with a force that's bigger than this value right here, then it's not static friction anymore. You've exceeded that value. You've exceeded the maximum possible value, and static friction is less than or equal to that value. So at that point, it's got to be kinetic friction, and you'd have to calculate the kinetic value right there. So what kind of question could you see on this? Well, in its most simplest form, an object is sliding on the floor. The coefficient of friction is 0.8. The mass of the object is 10 kilograms. Okay, we'd find the force of kinetic friction that way simply by saying mu times Fn. I think I said it was 0.8 times 10 kilograms times 9.81. Right? Easy question. Right? 98.1 times 0.8, somewhere around 80, 78, 79, something like that. If you saw a question that was that straightforward, 78.48, it would likely be a multiple choice question, right? Pretty hard to justify this becoming a written response question. How could you turn this into a written response question? Well, maybe the force of friction is we don't know what it is. Maybe we don't know that it's static or kinetic. Maybe we're told that the coefficient of static friction is 0.75. The coefficient of kinetic friction is 0.50. The mass of the object is 10 kilograms again. Let's say we apply a force of, let's say we have an applied force, two of them, an applied force of 40 newtons and an applied force of 200 newtons. In both cases, what's the force of friction? In both cases, what's the force of friction? Well, we don't know whether it moves or not, right? So we got to find out whether it moves. Let's get the maximum possible value first, using this equation up here. FSF max is equal to mu s times Fn. The maximum value is 0.75 times, on a flat horizontal surface, it's going to be 10 times 9.81. What does that equal? 0.75 times 10 times 9.81. 74.73 point something? 73.575 newtons. Okay, so we can't be any bigger than that for static friction. If we apply a force of 40 newtons, does it move? No, it doesn't, because we haven't exceeded that. What's the force of friction in that case? 40 newtons. If we apply a force of 200 newtons, does it move? Sure it does. What's the force of friction now? We're not sure. Now we've got to find the force of friction, kinetic, by saying mu 0.50 times 10 times 9.81. That's going to give you 49.05. So static friction in the first case was 40 newtons. Kinetic friction in the second case was 49 newtons. Does that make sense? What else could we do with friction? Remember, we've done a couple of these problems as well, where maybe you're talking about a highway designer. A car is driving around a turn with a radius of 200 meters. The coefficient of friction between the tires and the road is 0.8. What's the maximum speed that the car can travel on the road? Well, in that case, you're going to say the centripetal force, because it's going in a circle, right? The centripetal force is mv squared over r, but it's also caused by something. What would the centripetal force be caused by in that case? When I swing my keys around my head, it's caused by the tension in the rope. When the Earth goes around the sun, it's caused by gravity. When a car goes around a turn, the centripetal force is caused by what? Friction. So we'd say mv squared over r is equal to, in this case, we'd say mu times Fn, which Fn is m times g. Masses cancel. We'd end up solving for v there, or whatever it is that we were looking for. Okay, so there's three possibilities that you could see with friction. Okay, I'm not telling you, yes, friction is there. I'm not telling you, no, friction is not there. But I mean, we spent a fair bit of time on it, so there's a good chance that it's going to appear somewhere in some form, whether it's a more simple multiple choice question like this, or whether it's a more complicated written response question like this, or whether it's something that's kind of in between like this. Okay, there's a good chance that something is going to be there. Okay. See, I'm asking you guys now, what else do you think is going to appear on the test? Brendan just tells me, what about one of those problems where the car goes up and down on a hill? That'd be a great question. Be a great question for an exam. Be a great question to be, say, question number 8 on an exam. Hypothetically speaking, that is. Those are easy questions, right? Okay, especially when we're going over them a week before the exam, a week to the day before the exam. So you got a question like this. Okay, let's call this hill A. Let's call this hill B. Let's call this hill C. You know what? Let's not even label them. Okay, let's just make the heights here. Make it 20 meters. Okay, let's make this 15 meters, and let's make this 5 meters. Let's put a car at the top of this hill. Let's give it a speed of, let's give it 5 meters per second. I want you to tell me what the speed of the car is right here. And I want you to tell me what the speed of the car is right here. Okay, we'll make the first one in blue. We'll make the second one in green here. So let's find the blue one. Let's find the speed of the blue one. Travis, question? Let's find the blue one. Your question was going to be, what's the mass of the car, right? Yeah, in this case, we don't actually need the mass of the car because it ends up canceling out. Okay. Makes you feel more comfortable, though. Let's make it 20 kilograms. Okay. All right. Whichever one we're trying to find, whether it's the blue one or the green one, we're going to say EI equals EF. EI is the initial energy. And we know the mechanical energy is the total energy here. Okay, the total of kinetic and potential. The mechanical energy at point I is going to be made up of both kinetic and potential. Why? Because it's moving. It has kinetic energy when it's moving. Why is it potential? Because it has a height. It has potential energy when it has a height. What kind of energy does it have at the bottom of that first hill? At the blue question mark. Was it moving at the bottom? Then it's got kinetic, right? Does it have a height at the bottom? Case? No. So it doesn't have any potential, right? Now the masses will cancel here. And some people get a little bit confused by that. We got two masses on the left side and only one on the right side. Doesn't matter. Okay, you got to have a mass in every term in order to cancel out mass. We can do that, although if you want to plug in the 20 kilograms, you go ahead. 1/2 of, we're moving at 5 meters per second to start off. We're going to make the G positive because it's energy here. HI is 20 meters. We solve for VF there. 1/2 of 5 squared is 12.5. 9.81 times 20 is 196.2. 208.7 times 2 is 417.4. And the square root of 417.4 is going to be somewhere in the range of 21 meters per second. Let me find that, but we're going to get something like 21 meters per second there. Is that okay? Well, what if we were trying to find the speed at the green question mark now? Say the same thing, EI equals EF. EI would be kinetic and potential, the same as it was in the last question. And EF would be, this time, kinetic and potential because it's moving at that point, but this time it's also got a height. This stuff should be coming back to you from your West Ed assignment because you had to do this with your West Ed assignment, right? A few times. Masses cancel again because it appears in every term. Initial energy ends up being exactly the same. Just 2 seconds here, guys. The final height here is 5 meters. So we get 208.7 on the left side. We get 49.05 on the right side. We take the 49 over by subtracting. We divide it by 1/2. We square root it. I'm not sure what number we get here, but I do know that it's going to be a number that's smaller than 21 because it can't be moving as fast here as it is here because this is lower, right? Then I just gave you another 4 points on this exam. What are we at now? Like 20? It's a third of the exam already, hey? Okay. Maybe you want to show up tomorrow, guys. Okay, have a good night, everyone, and we'll see you tomorrow.